So aircraft systems are extremely complex and large, and so contain, I don't know how many uncertainties. And so Simon, can you tell us where you start with that problem? What's the first thing you do there when you're dealing with a very large structure and very complicated and has such a huge number of uncertainties? So you've mentioned sensitivity analysis, and one or two people have mentioned surrogate models. And I don't know, have surrogate models really been tried on very large structures with so many uncertainties? We know they work well on small systems, which we understand well. But when we get such large structures where we have uncertainties that we don't even know about, how useful are surrogate models?
We are using them. We are using them in early design phase. So yes, you can cover a large range of design parameters and uncertainty parameters, but with lower fidelity approaches. So quick tools, quick analysis. You're not going to be running CFD, structural analysis in this. So in the early phases, it's about breadth of exploration, recognizing there is uncertainty in my methods. My ability to predict the structural weight or the aerodynamic performance is uncertain because I'm using lower fidelity approaches. But you try and cover a wider range of possibilities. So remembering that uncertainty in aircraft design has always happened. Ever since we've been designing aircraft, engineers have managed uncertainty in aircraft design by engineers being engineers and putting in conservatism, safety margins, gut feel, whatever else. We have designed safe flying, well-performing aircraft in the past. So it's not like we don't do it, but it's engineers with lots of experience and lots of knowledge of challenges from previous aircraft, things that have gone wrong, things that we want to not do again. So this is typically how it's been done. As we get more into computational ability, we are now looking to simulate more and more of that aircraft. So more and more of the different options, we are able to simulate that. We're able to use surrogate models as a tool. Again, remembering a tool to inform humans to make better decisions. Okay, is that part of your question?
Yeah, anybody else like to contribute to that conversation?
Really difficult to know, because if you haven't done the analysis, you don't know whether it's important or not. That comes from engineering expertise, judgment, previous experiences.
Yeah, I believe this is precisely where the role of the engineer comes in, but the role is no longer run the simulation or a single one or multiple simulations, but the role of the engineer, the way I understand it, having all these tools of surrogate modeling and high fidelity simulation at hand, is defining the right bounds and setting the right settings at the right time to get reasonable and reliable results. This will not always work out, but I mean, that's the experience you have to learn over time, but it's no longer learning to do a few deterministic simulations and then interpreting this somehow to get a result, but to define settings for a probabilistic approach and then understanding that result. So I believe the engineer is not, or is still needed, maybe even more important than that, but the role will change. So the influence and the role to define will be different, and he becomes the one guiding the process and no longer doing the process step by step. That's the way I believe it. And that's the way how people have to transform to make the most out of these tools that are readily available. I mean, number crunching is for free now, as long as you crunch the right numbers.
That's an important part of that. Whatever we do in terms of our analysis, our uncertainty analysis, computation analysis, using more and more, we generate data. Data has to be converted to knowledge and understanding. So this is where the human comes in. Computer doesn't give you understanding, it gives you data. So the human has to take that, and what does that data mean to the decisions I need to make? So this is where the human now is, as you say, probably less, we're trying to move less to I'm pushing buttons and running simulations to
I can now compute lots of things. I now need to understand what does that mean to the decisions I need to make. So you're changing the emphasis.
But surely we're not, I don't totally agree that computing is free,
It's not.
but surely we're not at a stage where we can just run a Monte Carlo simulation where everything be available.
So that's where surrogates come in, and sampling still, I think they're going to be an important tool.
Give you an example. Simulation. So we talk about cloud simulation now. Everything we run on cloud. Airbus is moving to a cloud environments. But CFD CSN, so a high fidelity kind of prediction of our aerodynamics and structural coupling. If you wanted to run 1,000 of those in a nice design space, it will cost you about $1 million in Amazon Web Service to run that in computation cost. It is not free. So typically, you're not going to run 1,000 CFD simulations, but this is it. It's not. There is still a cost. Cursor dimensionality and high fidelity simulations are not free. You can with cloud, you don't pay the time penalty. You can probably have the results quite quickly, but you are still paying Jeff Bezos money.
But then again, is it that 1,000 simulations are going to capture your domain, your multidimensional domain? So I can't help but hear one recurring word, and that's probabilistic. What about just general non-deterministic? I think there is a subtle distinction here, right? I mean, it's not dwelling on probability distributions, but general descriptions of uncertainty. So perhaps the right way to go, or a way to go, is to make or to do UQ in a smarter way instead of do more of it. Instead of just investing into sampling and trying to understand those distributions and invite experts to describe those distributions.
Yeah, you still need the role of the humans now is better understanding from. You don't just blanket scattergun shot. I've got 3 simulations, let's do everything. You still need a human in the loop to determine what is important.
Right.
Maybe a question for you, Peter. You spoke nicely about safety factors, and I mean, we already heard that safety factors are well established. Engineers know how to treat safety factors. Decision makers know how to treat safety factors, and also certification authorities know how to treat safety factors. Now, at the end of the day, I mean, doing UQ is not something we do for the sake of doing UQ. We want to get some added value and added benefit out of it. And I'm always struggling to see a clear way forward to not simply add more computational cost to everything, assign some probability bounds, in the end up with probability bound on the results, on the safety factor, in the end still have the safety factor, and everything simply becomes more expensive and probably more conservative for the same result, or a very similar result to what we have right now. I mean, you showed 70 years of aircraft, but they're all flying, they all got better. So what's the way you see forward to overcome this conflict, if there is any, between safety factor and probability and the mindset associated with it? I mean, safety factor is a fairly comfortable mindset, I would say.
Yeah. I could perhaps attempt an answer with a question. There's something that John said in one of the previous discussions. Can we develop the same level of trust in UQ as in safety factors? And I would question this with, I would ask a question: what gives you the trust in safety factors? Why do we trust them? You say that certification authorities and engineers know how they work, but do they actually know how they work? Do you know what's happening? Do you know what uncertainties are you covering for when you stop safety factor of however? I think it's something rooted in tradition more than really understanding. If you
trust, it's hard to obtain.
Yes, of course.
And I think it's very hard to obtain by hard-nosed engineers like Simon in the industry who have to make things work. And you know, we heard about the cost penalties that come with these things. So you know, that trust is very difficult to achieve. And you know, I mean, how much can we believe on, you know, computations that have been done? I mean, are you suggesting that you use a probabilistic approach and you do this independently of engineering knowledge, which has been built up on generations and resulted in safety factors, and can we really believe that that's going to give us an advantage?
Not at all, but not at all to exclude the engineer from the loop.
No.
In fact, yes, in fact, the non-deterministic sequence of numbers that I showed tries to incorporate knowledge. It tries to, what it tries to exclude from the loop is injecting artificial assumptions. So if you know something to be a fact, then you should be able to specify more. That is the way forward. It's not against experts or opinions, if that makes sense. So it's just very often, I mean.
Yeah, I think the engineering knowledge, engineering understanding is a vital ingredient.
Of course it is, of course it is. We saw in one of the examples, I think the first one that Jonathan showed, uncertainty, quantification of different things, everything was normal. Everything was normal distributions. Is it really normal distributions?
No, it's not, no.
So,
But that was generated from multi-algorithm.
exactly. So, you understand Gaussian process, right? So that comes straight from your assumption of using a Gaussian process. So, that's
So
those
the other
those
ones,
things. Sure, of course.
yeah.
So the other thing, Peter, one of your slides, you showed sort of generations of aircraft up to the modern day.
Yeah.
And you said, well, this is the disadvantage with safety factors. You know, it's incremental, but they're all these airplanes, they look like the same shape. And the probabilistic approach could allow you to be more creative. Is that really true? Is that, Simon, do you think that's really, or do you think that's just an exaggeration slightly? At least slightly.
Just a bit to you answering is that that's my feeling. I don't have scientific proof to substantiate, but you know, you look at all these things, and I know like hundreds of aircraft, they look the same, you know, in certain aspects. So
I'm playing devil's advocate a bit here.
But I mean, on the certification side, the kind of ability to challenge some of the safety factors is not simple. You mentioned some of the things that are covered for certain safety factors. A lot of it is also uncertainties on the operational use of the aircraft. So one of the things that, for example, if you want to challenge some of the requirements of either the certification requirements or the safety factors, there's a question of what is that covering? What scenarios of real operation, for example, you know, weird cross-coupled landings, crab landings, high gust winds, we don't simulate those because they are covered by the safety factors. You don't need to simulate those in the requirements because the safety factor covers those operations that are non-standard. If you start reducing those, it puts a lot more emphasis. Then you have to analyze all the potential things that happen, which we don't.
Yeah. Okay. Yeah. So I think the safety factor is, as I said in my talk, is essentially a blanket. It's a lumping of the uncertainty.
It's a comfort blanket.
Yes, it's a comfort blanket. Yeah. So
Is this something to be said about dealing with like low fidelity models compared to like more complex simulations of, as you are increasing all of these inputs and introducing more information about what's going on, if you're doing it either probabilistically or with some non-deterministic method, there's layers upon layers of dependencies that you then also need to take into account. And if you can't do that, you might not necessarily be improving your ability to make decisions by increasing the fidelity if you don't actually have the information to do that in a robust way to account for the dependence. So it might be that because of the limits of your knowledge that the lower fidelity models may be better in terms of probabilistic or non-deterministic analysis.
Also an interesting concept that, sorry, some of the lower fidelity models that we use are typically heavily calibrated against certain things that we know. So things on the actual aircraft that we've delivered, made, and everything else, we are calibrating them to things we know. When you're dealing with first principle simulations, they're going from the physics. So they're not necessarily calibrated. And there's a question that actually sometimes higher fidelity simulations aren't better. Yeah, because you're simulating something where you've missed some aspect of the real world design that is captured in your simple methods because they're calibrated against real aircraft. And this is a very difficult thing to actually get your head around sometimes, that the high fidelity methods aren't always better.
But I mean, that's precisely why we are stuck in this 70 years of the same thing. So I believe the first principle ones are not perfect, but they do have the potential to move forward, and there UQ might play a role, while the calibrated ones are essentially ensuring that you stay with the 70 years of knowledge you have, because you know if you deviate from it, these are pretty much rubbish. So I believe, yeah, there are cases where the simple methods, if you simply tuned all the numbers right, kind of fit to what you have right now. But if you think ahead, then they probably don't fit any longer, and then you're in no man's land. While first principles do offer a way forward, knowing that they are not perfect. So it comes down to model form uncertainty at the end of the day, probably, which is a very hard nut to crack. But still, that's where I would say it's worthwhile to add research, and probably that's currently at the research level and not at an industry level. Yeah, I would like to make one additional comment. We're speaking a lot about engineers, but I believe in general, mindset also has to change beyond engineering, because typically when I and I believe it's the same for Simon, start to speak to people, at some point there are no longer engineers, but then they are typically the ones making a decision or having the money. And then you still have to convince them that this is sound, that this is reliable, and so on. And certification authorities are not all engineers. There are lawyers, for example. Yeah. So it's more a general mindset change which goes beyond engineering, and probably has to start at a university level or already a school level, and not in your industrial career or so later on. So yeah,
it's coming down a lot to the believability. So I have to understand and believe the system in order to be able to take that on board with my decision.
Yeah, and that's the point. As the trust, I think, comes with a certain calibration. It's something distinct from model calibration, but to be able to show that your uncertainty bands are not small or large, that doesn't matter so much, but they encapsulate your true answer, that as will get unfolded in the design process.
I think it's very difficult to challenge those safety factors, certification safety factors. You said, are they correct? Well, they're working at the moment. We know they're working at the moment. So now we don't know if 1.5 is the limit. It may be there's something else, but we know 1.5 works. So to challenge that, you then have to model everything, all the cases we don't look at now. And so it's a really difficult thing to go for. But there is an area you can challenge, which in all the design process, we add margins everywhere. And these margins are added on twice by different groups all over the place. And uncertainty quantification could challenge some of those margins we add on for performance, for things which aren't safety related. I think that's very much where UQ could change that and change how we design aircraft and design wings. We have different uncertainty on different aspects and the design we have, then it may change some of those margins we put in. And that may change how we design new types of aircraft, new types of wings. If we have a different UQ understanding of a given design, we may find we actually stay with the traditional design because we know more about it. But that's the question that could be there. You know, there could be more uncertainty margin put on the ones we don't know about, in which case it pushes them further away. But if that's where we are, people do that naturally in their judgment. We could do it from a point of view of calculation as well.
If you put safety margins in stuff that is performance related but not safety related, wouldn't that propagate through Simon's complex dependability relationships through safety ultimately? If that makes sense.
Say that again.
So I think Kevin, what Kevin is saying is that instead of trying to challenge the safety factor, we go for challenging the performance of the
margins.
The margins on performance, right?
The soft constraints.
Sure.
The hard constraint is got to be safe. That's hard.
So
you can't challenge that.
right. Yeah.
But performance, if it burns 7 more fuel, in the end, it just costs a little bit more. It's not a really hard constraint. You know, yes, it becomes hard when we sign a contract, like you said, and within that contract, there's a big margin because we know there's uncertainty.
Exactly.
So that's where we can take it out when we do that initial design. Can we reduce that uncertainty to the guarantee that we're giving?
Sure.
In which case we end up with a better product.
Sure.
That is one area we have applied
Q2, of course, performance guarantees, it's an area we've done something on.
Very good. So yeah, I think I got you correctly. My question was that those soft constraints, once you apply UQ to them and start modifying margins, wouldn't those new margins propagate through the design to the hard constraints, or you think these two things are totally independent of each other?
I would say the UQ formulation is what is the confidence in being able to demonstrate compliance with the certification requirements.
Sure.
So that's the ultimate thing that we're trying to. If you typically in everything I've done so far, we've taken the certification process and the safety factors as fixed, and the uncertainty is our ability to demonstrate that compliance and meet our performance objectives.
Yeah.
Okay. The certification becomes essentially a constraint that we have to achieve.
Right. But a hard constraint.
It's a hard constraint,
Right,
but it's also an uncertain constraint. So the constraint is there, but the means of compliance is uncertain. So our loads are uncertain, our structural size is uncertain. So we have to demonstrate this at the end. But in the early phases, it's not sure what that is, but we know what the requirement is. It's uncertain of how we are able to demonstrate it or design the aircraft to be able to demonstrate it.
This other constraint, which are more, things you can't change later on. When you said you come down and you can't really change. Geometry is one of those things you can't change. You've got a certain size wing, you've got a certain size movable on the back of the wing. It's very difficult to change those. But changing the size of the structure, you know, the max takeoff weight of the aircraft, you can change those quite a lot later on, which we do. So you've got to look at which are constraints are actually things that you think once you've fixed at the beginning of that design process, it's very difficult to change after that.
Simon showed his picture with the levers. Yes. Where it was a very conventional what size thing, and then we'll do the aerodynamics, and then we'll do the structures, and then we'll do the controls. Is there perhaps an opportunity with this UQ to sort of start designing everything together? Yeah. Yeah.
More and more fidelity. So you get a bit of a current notion. So yes, we will have to go into this to look at some higher fidelity, to look at in early phase size of wing, but there's a limit to what we can do. We are trying to get much.
But again, it's understanding what is the right fidelity of those levers to be incorporated to make today's design decisions. And you don't simulate everything. You need to simulate sufficient to ensure that you've got the right aircraft definition, which is not easy.
Would it be beneficial, or would you have, maybe you have done it in the past already, to have a sort of assessment of a previous design, a well-known design, and trying to compare the safety factor approach with a more elaborate sort of uncertainty quantification approach to see where it would have led, or maybe to see if the decisions would have been the same at a certain point. Of course, it depends from.
So are you talking about the challenging uncertainty, challenging safety factors, or
toward convincing or building trust, having some sort of comparison within the two approaches in a known design. So a previous aircraft, for example, one of your aircraft, you just go through, you assess the design process, take into account what has been done before, and compare it with something that you want to introduce in the future, and see what it would have led and which benefit it would have generated.
So redoing that design process
Instead of looking at the safety factors, actually doing a more probabilistic assessment. So this is almost challenging the certification requirements. So saying rather than meeting my safety factor, I look at my probabilities and safety. It's a very difficult thing to do, but theoretically possible.
Maybe be a way to prove or disprove what it can do, or what it can do differently, what it can do better, to convince and build trust.
It's possible. I still feel, and kind of with Kevin on this one, that where I see it at the moment, the biggest opportunities are more not in the challenging the certification requirements, but in the how we design aircraft to meet the certification requirements, how we manage the design cycle and the application of margins and targets and things that we do with a fixed certification basis. That's where I see the most opportunity today. But given this is longer term,
so yeah, can we have about 8 minutes to lunch. Perhaps we can give the floor to people online. I am going to read the questions, if you don't mind me doing so, so that our audience here can maybe answer them. So Marco asks, how much work is done in Airbus to study the traceability of aircraft design? What do we know of an aircraft that has been manufactured? I mean, can Airbus access those metaphoric levers that Simon presented that were pulled since the very early design a posterior, so later on? Are there commercial constraints to doing such practice?
That before of looking at our existing aircraft design processes and going back. Theoretically, yes. In practicality, it becomes very complex because there's lots of decisions and inherent things that are made to unpick. It's very difficult to compare, to make a clean assessment, because there's lots and lots of things going on in parallel to understand pick out a clean process, if you like. So
you need a rationale capture type of.
Yeah. I don't know. I'd have to frame that problem a little bit better.
Okay.
But historically, going through, if you kind of look at going back through historical projects of what happened when and what did we predict in the early phases and what did we end up with, lots of things change in the rationale from when we fix things in the early phases to the final aircraft. Lots of things have happened in between for a variety of reasons, but maybe that's part of the uncertainty process. This is what we're capturing. I don't think, and I'm with Kevin, you and I mean, we've gone through and looked at that, of going back and saying, yes, we do lessons learned.
It's not working like or something's found not to beat the requirement with the margin we've got, then there'll be a deep dive into that and asking what questions, why did that happen, all the way back to the beginning of the design process, to learn from it, to change the margins we're putting in, which is that experience we're getting. Each aircraft design we do, we learn, and then we put that back into the beginning as that sort of quantification of uncertainty, saying, well, we missed it, we need to put a bigger margin here, or change the design processes. Obviously there's that as well in terms of the methods used and all of that, but it can be just, yeah, we know this value we can't predict, we need to do something about it.
Sorry, can Edmar, so I'm sorry to interrupt. We have limited time. I want to give the word to Professor Patfield in a second. I'm just going to read the second question, and then I'll pass it on to you, and then we can carry on the discussion. Apparently, there's a lot of interest in this. Okay, so Chris Linus says, I don't want to, well, okay, he doesn't want to interrupt the discussion. I don't see UQ as a way to get better performance by challenging safety factors. Rather, the priority for me would be to make better product decisions, perhaps with better knowledge of things that we find hard to include now. The main requirements challenges I'd like to understand are customer requirements to ensure we're actually meeting what airlines need, not safety ones. So it's performance again, if I understand the question correctly. Anybody would like to offer a comment on that? I suppose that's as much of a comment as a question. So.